Hello and welcome. Today we'll be presenting the 2003 North American Blackout. Let's meet the team.
I'm Dale Carrar.
I'm Victor Beator.
I'm Luke Forbes.
I'm Amy Huang.
And my name is Jack McCove. On August 14th, 2003, which started out as a very typical day, turned south when over 50 million people went without power in the northeastern region of America along with Canada. The day the power went out, there was over a 60,000 megavolt load that was not met on the electrical system. The US economical loss at this time was between $4 billion and $10 billion, and Canada lost 2.3 in manufacturing alone. How this happened? The blackout happened with some very small incidences that compounded throughout the grid with lack of communication amongst other grids and seemingly misseemed small incidences.
Oh, here are some of the methods to prevent future blackouts. You can evaluate the power voltage control practices. You can improve the system to slow and limit future cascading outage spread. You can evaluate the lesson we learned and install some time-synchronized reporting device. Reevaluate the design that we currently have and improve the system data and the exchange practices. Next slide. Okay, so to evaluate the power and voltage practice, we can identify inconsistent practice in northeastern Ohio, which is where it happened. And you can do this through setting and coordinating voltage limits and insufficient reactive power supplies. And you can also require each region to establish procedures for generating data, verification, and testing. And the generators must keep the network voltage or reactive power output within the reactive capability.
So how do we improve the system to slow/limit outage spreads? Well, we can have two different ways to improve grid reliability. Firstly, we can use phaser measurement units, which would measure the voltage, the current, and the frequency at different points in the grid, which provide some synchronized data at real time that would help prevent the outages to spread. Another way to improve grid reliability would be to use demand response systems, which would balance the supply and demand of the electrical load and overall reduce the stress on the power grid, which is just an additional tool to manage disruptions. So what are other methods we could use to improve the outage spreads? Well, we can use backup powers, and this could come in the form of fuel or solar, but there are some advantages and disadvantages for each. For instance, fuel's advantages is that it's reliable, efficient, and has a long lifespan. However, the disadvantages is that it has negative environmental effects, and it is vulnerable to the fuel supply chain, which means if the supply chain for the fuel somehow goes down or there's not enough fuels being supplied, then obviously the backup power would not be working. For solar, the advantages is that it can be implemented with power grids, with microgrids, and has low maintenance costs. The disadvantages is that at nighttime the power reduction is reduced and it requires mineral extraction in order to create the solar panels. So this is an example of innovative technology, which is basically just a resilient power grid at Seattle. Basically, Seattle had a project at the Miller Community Center, which it costed around $3.3 million to install the microgrid in conjunction with 132 solar panels. So these solar panels were each rated at 43 kilowatts PV solar panels, and the advantages of this example is that it created job opportunities for the microgrid installation, basically improving the economy of the location, and it also significantly reduced the energy demand. So that's why it was beneficial. Researchers have also determined that applying a similar approach at Cambridge could have its energy demands with only 20% solar adoption, which is why innovative technology can be used in this manner. And this picture shows how the Seattle Community Center employed the solar panels in conjunction with the on the top of the rooftops of the houses or just community buildings in order to achieve this.
So speaking more to how the 2003 Northeastern blackout occurred in the first place, pretty much the largest component of it was cascade failure. So basically, when one component fails, usually due to natural disasters, it can lead to other components failing that are connected to that one component. So essentially what we see is, for example, let's take a transmission line. If we have one transmission line on a power grid, that can collapse due to, let's say, a natural disaster like a tornado, an earthquake, or any such example you can think of. That can cause the load on the other transmission lines that are servicing the same power grid to collapse as well. And once those collapse, it leads to a snowball effect where the ones they're connected to will collapse, so on and so forth, until the entire power grid is down. So when it comes to the, So when it comes to the Northeastern blackout, imagine that this system here is a transmission line in Ohio, for example. If this transmission line goes down due to, let's say, overgrown trees, which is what happened in our Northeastern blackout example, then when this fails, these 90% loads are going to have too much strain on them as well. Then these 90% loads can fail as well, which will cascade into the rest of the system failing. So you can see how quickly things can devolve if the load isn't reduced in time and things can get out of control. Next slide. So to get into the more specifics, the 345 kilovolt transmission line was the initial breakdown of the Northeastern blackout. So a transmission line in Ohio had an outside factor that caused it to collapse, which was an overgrown tree. So due to the heat of the summer, obviously it was August, it was the dog days of August, very hot. This caused a huge amount of load to be demanded due to like air conditioning requirements, and basically the hotter the day is, more often you're going to need bigger load, and it's going to have more physical strain on your transmission system. So we can see why the outside factor caused our first failure for our first transmission line, which was due to overgrown trees and heat on the transmission line due to the heat of the sun. So right when this transmission line went down, the load was already 1,500 megawatts above what the system could support. And this can be seen in specific transmission lines, such as the Star-South Canton line, which was already operating at 120% of its maximum rated load. So before the collapse, it was at 82% due to the heat, but that's still within reasonable levels. But after the collapse, we're starting to see the loads are not decreasing, and they're being transitioned to other lines, and these other lines are not able to handle it. So once the emergency threshold is reached, maybe a line can last for 5 to 10 minutes, but they're going to start collapsing one by one. And as one line collapses, another line will collapse. And this will add more and more load to the line still functioning until eventually the entire system collapses. Next slide. So here we see a timeline for the 2003 blackout. So we can essentially see these first few collapses are due to failures when it comes to contact with overgrown shrubbery, overgrown trees. So once this first line fails, it's going to cause more heat on these lines, which will make it more likely they sag, which makes it more likely they contact trees, which makes it more likely that they short and trip. And once we get down here to 1605, so about an hour and a half after the first line fails, we're starting to see failures that are occurring with absolutely no outside force whatsoever, which is due to the massive amounts of strain and massive amounts of load on these lines. In our research, we saw that it can go to a maximum of 180% over the load that the line is supposed to handle before collapsing.
I'd just like to add to that last part though, that the line started initially overheating, and that's what started hitting all the trees, and then all the other lines started overheating to make it a whole cascade effect, like Daniel said.
Yeah. So continue?
Yeah. Next slide. Yeah.
So just one more thing about the probability of cascading failure. a big thing that we researched and that we think would be a good suggestion for the future of power grids is to be able to determine which lines are in the most danger of causing cascading failures. And that's the places we need to focus on and make sure are as reliable as possible. So the research done on the Northeast blackout concluded that about 11% of the Northeast power grid that failed, 11% of the transmission lines, and 11% of the failure rates, like the components that could fail in general, were at risk of causing a cascading failure. So essentially what we want to do is we want to limit this statistical probability as much as possible. We either want to make this extremely low, or the alternative is to make sure that even if it stays at 11% or higher, it becomes extremely rare that a component does fail in the first place. But the ideal situation would be to be able to limit load in such a way that if something does fail, the other lines aren't strained to the point where they fail as well and causes this snowball effect that we saw during the 2003 blackout.
So here are some alternatives set up that can help prevent future blackouts. You can have a smart grid, which incorporates a network approach that supports two-way flow of electricity and information. You can also invest in distribution automation, and it provides utilities with increasing capabilities. It does have a very important feature, which is self-healing feature. It provides real-time monitoring and reaction, anticipation, and isolation, just in case something goes wrong. It will be able to be dealt on its own. You can also manage the grid in real time by automatic monitoring. The two-way communication can offer instantaneous information, as mentioned before. It also allows the consumer to interact with the energy management system, such as smart metering, which receives power consumption info from appliances like your TV or your fridge, and send over control commands.
So, forecasting other potential blackout causes. The common reason for most of these is from natural disasters and stuff that you just are not able to completely predict, but you can continually take preparations for it, and they're extremely hard to foresee. So, like the natural events and stuff, they continually try to improve on making it so it's less likely for blackouts to occur. Say in the U.S., we've continually upgraded our lines to continually lessen that possibility, and improvements are continually being implemented to stop the possibility of causes. Next slide. So blackouts usually occur with hurricanes, snowstorms, and stuff, as seen in Florida. Hurricanes all the time, they cause blackouts, tornadoes as well, and floods. They're things we can't really do much about. The danger of targeting specific regions is more aligned with the likelihood of these natural disasters to occur. So, yeah. Next one.
So to conclude our presentation, we have determined that power blackouts of this level are very rare, but their consequences are very severe, which means that we have to properly improve our power grid in order to avoid this from happening. So one way to reduce this, as mentioned before, would be to increase the reliability of the power grid by having a balancing the electric demand and supply, which obviously would reduce the demand on some other power lines after one of them starts falling down. And we have also seen that advanced power systems have used other measuring units such as the PMUs in order to track this data and actually use preventive measures before consequences get severe. Next slide. These are our references, and that's our presentation. Thank you for this semester, Dr. Lee.
Thank you for this semester.
Thank you.
Thank you very much.
Yep.